In this video, we're going to think carefully about one idea, partial derivatives. By the end, I hope this idea feels simpler and more connected. So, in single variable calculus, the derivative is mathematically, we write it as f prime of x is equal to limit as h approaches 0 of f of x plus h minus f of x over h. This is the definition of a derivative in single variable calculus, where y equals f of x. As you already know, derivative is just, it measures the instantaneous rate of change at a specific point of a function. In multivariable calculus, the core idea is still the same, but just multiple variables, that's it. So in multivariable calculus, the definition of derivatives are, let's say, for z equals f of x, y, it's multivariable functions. The first order partial derivatives, partial derivatives with respect to x and y are we denote it as partial z with respect to x. This is the same as f sub x of xy, and this partial x is equal to limit as h approaches 0 of f of since it's a partial x with respect to y, which means the variable y is held constant, it's fixed, so x plus h and y minus f of xy over h. That's it, very simple. And partial z over respect to with respect to y is equal to f sub y of xy. They are the same, just different notation. And this is equal to limit as h approaches 0 of f of x and y plus h minus f of xy over h. So mathematically, this is the definition of derivatives. Specifically, it's called partial derivatives because we partially find the derivative in x direction while y is fixed, or in y direction while x is fixed. So basically, the fundamental idea of finding derivatives is still exactly the same, but we are looking at a partial, the part of the surface. So geometrically, you can think of it like you slice the surface and look at a curve. That's it. All right, we just talked about the definition of partial derivatives. Now I want to talk about a bit more deeply about what they actually mean. So interpretation wise, partial x it gives us the instantaneous rate of change of f in the positive x direction with y held constant. So we are interested in the slope, the rate of change in the x direction, but y-axis is fixed, like a constant. While partial y gives us the instantaneous rate of change of f in the positive x direction, positive y direction, um, with x held constant. So it's like the opposite. So we are looking at the instantaneous rate of change of y direction, and x is just like a constant. So it is impossible to find like I don't know how to say, but like the overall like one derivatives like overall rate of change of the surface, but we need to kind of split in two directions, and we find x and y directions, and um, we can kind of look at them at the same time to see the overall interaction. Actually, we are going to talk about it deeply in the next video, which is second order partial derivatives. So using first order and second order partial derivatives, we can actually see the shape and like the how the surface look like, and how the curvature um, changes. So we can analyze the curvature and the shape of the surface using both of the partial derivatives. All right, that's it for partial derivatives. It's a very simple idea, right? Actually, I wanted to talk about just one more idea really briefly. There's a theorem which says if partial x and partial y exist near a point AB, and if they are continuous at the point AB, then the function f is differentiable. It's pretty interesting. What it means is that the fact that the continuity of partials guarantees that the function f is differentiable. So continuous partial x and continuous partial y, both of them, means that there's no sudden jumps in steepness at the point AB. So the surface at the point AB is smooth enough so that it gives us the enough differentiability condition. So we can draw a unique tangent plane at that point of the surface, so it is differentiable. It is so useful theorem, and it just sounds so like pretty interesting. So I wanted to share this, but you don't have to memorize this. Today we focused on first order partial derivatives and differentiability. Next time we will look at second order partial derivatives and what they tell us about curvature and shape. That's where things get even more interesting and very like complicated. So please be excited, and until then, let's keep things simply connected. Thank you.